Right, well, welcome back. And if you've been following my videos, you'll know that we're very close now to doing branching in the computer. So the only thing that was missing was the decoder card. So I've got the old decoder card here, and basically this one at the moment can decode ALU, move 8 or set AB instructions, which is great, but we need to add go to it now. So what I have, as with the other cards, I've got the old one here, and we've got a new card here. So this really is one of the simplest cards going, really, because it's only uses 5 relays to decode then the various instruction classes down the bottom. So it should be quite easy to solder together, and then we'll just give it a quick test and then pop it in the computer. And with that, we will then be able to do some simple branching examples. And what I'll do for this one is I'll just do a quick counter example where it just keeps counting up a number. Just as a basic example, and what I'll do is I'll save something a bit more complicated like the Fibonacci sequence for a summary video, because it's been a while since I last did one of those now, so I think the computer's reached a point now where it's worth doing a full summary. Anyway, right, let's crack on. So for this I'll just need to just do a quick bit of soldering, so I'll do this as a time lapse again, or as a bit of footage, just so you can see how it's all done. But you can see this one's going to be really straightforward and really easy. Right, let's get on. Okay then, so that's that's the card complete. So you can see that didn't take too long at all actually, about 24 minutes in on the original video. So yeah, probably one of the simplest cards I've had to do so far. So nothing much remarkable to say about this one really, so we'll give it a quick clean up and then I'll chuck it in a test rig and we can quickly just test it works as it should do. So here we go then, we've got it in a quick test rig and really simple to test this one this time. So I won't do a close for this, but effectively you have the instruction bus coming on the back here. So that's the controlling instruction bus, but it's only the 8 bits of the instruction bus we're interested in. And basically that will come through to these switches here. So that'll allow me to set the effectively the opcode that will come in from the instruction register. And then coming out is basically the op bus. So that's where then we'll set the class of instruction, which is basically what the decoder's job is to do. Nice and easy as well. We've got power on here as well, so it's very easy to hook up the power to the card. So without further ado, let's go for this. Now also I'll be covering all of the instruction classes that it does. So although on my blog we've only really talked about the GOTO, Move 8, LU and Set AB instructions, actually there's a lot more instructions we can do. So in total there are 9 instructions that we'll be implementing later on. So I'm going to test those instruction classes, but don't worry too much about what they do because I will definitely cover those later on. And at the moment the controller can't do them, so the controller has a circuitry for them, but I haven't put the relays in there yet. And again, I'll start introducing those instructions later, but it should be quite quick to do actually. Right, so let's start by putting the power on. And straight away, by default, it starts up in the Move 8 position, which you can see just down here. And the reason for that is because anything that starts with a 0, 0 is a Move 8, and basically we've got 0, 0 here, so that's the one default position. Set always begins with a 0, 1. Actually, sorry, what I should just say before moving on to that is that although it's 0, 0, if I go for all the other bits of the instruction, you'll notice it ignores them all, and that's by design because then all the rest of those bits are for the basically for the parameters of that instruction. So if we go for the set AB now, so it starts at 0, 1, and then we get the set AB, and that comes through on the block here as well. And again, then all the rest of the bits of that are completely ignored. Next up is the GOTO. So if we do that, that's 1, 1. And again, all the rest of the bits are ignored, which is perfect. Cool, so that's the easy ones. So where it gets a little bit more interesting is when you go to the ones that begin with 1, 0. So 1, 0, 0, 0 is now a U function, and all the rest of the bits will be ignored. If I go 0, 1, 0, 0, 1, then we've got a load by default, and that's because it's 1, 0, 0, 1, 0 is a load, and the last 3 bits will be ignored, but a 1, 0, 0, 1, 1 is a store. And again, the last 3 bits are ignored. So this is basically where you can load and store a value into memory. So that's fine. So then the 101s, by default, a 10100 is a 16-bit move. So again, then the last 3 bits are ignored on this card because they'll be the parameters. And a 1011 is an increment XY. What I should just say as well is if I go for a 10101, that's a MISC, and that's basically where I'll have a few additional operations. And again, the last 3 bits of those are ignored. For the increment, all the last 4 bits of those will be ignored. And that's it. What you may have noticed on this block here, if you were watching closely, is that the Move 16 didn't light up this block, and this is because it's only looking at the top 8 bits of the op bus, and actually the Move 16 is on the next 8 bits of that. So basically, if I move this, in fact, I'll demonstrate it. So if I put in a Move 16s, that's a 1, 0, 1, 0, 0. So that's a Move 16. Nothing's lit up there, but if I move this block over, so I'm basically taking off the first pins and moving onto the back, you can then see the Move 16 comes through as the first bit there. Just show there's no cheating. Okay, that's it. So let's put this card into the computer and then we can try and do some operations involving GOTO, Set AB, LU and Move 8, which are our 4 instructions. Right then, so let's put the new card into its home. First thing I need to do as well is just put the legend strip on this because it hasn't got one currently. So let's just do that now. There we go. And in it goes. And she's ready to go. Right, okay, so first of all, let's just quickly test the decoder back in the machine again. And I know the only things I'm going to actually get on here are the 4 main instruction types. Let's give them a test anyway. So switch the computer on. And again, by default, we see that the move 8 is selected here and here. So I know that if I do a 0-1 instruction, and if I load that directly into the incrementer this time, so I'm going to select the data switches and load the instruction register rather, I can see then that this has chosen set AB, and set AB appears up here, which is exactly as it should be. So that's that one, so that's from the move 8, the set AB. We know that 100 will be an ALU instruction, so again I can set that up, so I'm going to select the data switches, load that directly, and that's great, ALU down there, and ALU shown up there. Brilliant, so the last one then is the GOTO, so that's 2-1, so select the data switches and load the instruction register. And in this case now we've got the GOTO down here, but up here it's showing but it's not lighting up the thing here. And that's more than likely because it's just not wired it up at the back. So what I'll do is I'll quickly just check up for that and just wire that out. And then I think we've got everything we need to do a quick program. So before we can run a program on the computer, we need to design it first. So I think what I'll do is a nice simple example of a countdown program. So we'll just count down from 10 to 0, and that should use all 4 instructions we've got in the computer. So let's start off with a basic outline of the program. So here's some pseudo code that just says we'll start with a count of 10 and then just subtract 1 from that count and keep on doing that whilst that count's greater than 0. So that's a basic outline for the program we're going to write. And now looking at the architecture diagram on the right, which shows how the computer's made up, you can see that there's nothing called count there, so that doesn't really relate to that diagram very well. So what we'll do is we'll take the pseudo code and make it more specific to this architecture. So there we go now, so we've said okay, we're going to use register A and set that to 10, and then we're going to set register C to -1. Now the reason why we're doing that is because the ALU can't do subtraction, it can only do addition. But if you add -1, it's as good as subtracting 1. As far as the loop's concerned, we'll move the value from A into B, where the ALU can get at it, and then we can do A equals B plus C. And then once we've done that, then we can keep on going round that loop whilst A is greater than 0. Okay, so let's take that a step further. And we'll start using some specific opcodes that we've got. So the set A equals 10 is easy enough, that's just a set AB instruction. Set C is a little harder because set AB can't do the C register, it can only do A or B. So what we'll do is we'll set B to -1, and then we'll copy that value over into the C register, which will have the same effect. Loop wise, again, to set B to the A register is just a move 8 operation, and doing the B plus C is just an ALU add, because ALU will always use the B and C registers as inputs, and keep on doing that while A does not equal 0 this time we've put, because actually again we know that the GOTO instructions can deal with things being 0, being not 0, or the carry or sign value set, which you can see on the right of this diagram here, where you've got the 0, carry and sign ALU registers. Right, okay, so we've got that. So what about that looping? Well, to do that we're going to need some line numbers. So the first 3 lines of the program look exactly the same, but this time once we've done the move 8 and then the ALU add, the GOTO will basically say we'll go back to line 3 if you're not 0, which is simple enough, but you need those line numbers so you know where to go back to. Last line then is just the infinite loop again, because I've got no way of stopping the computer, so I just want to put it into an infinite loop. So that will just basically say go to line 6 regardless. So there is a slight problem on this program, and it's to do with the line numbering at the end, because you can see the GOTO on line 5 is immediately followed by GOTO on line 6. But we know that's not the case because actually each GOTO instruction has to be followed by 2 bytes to give the high and the low part of the 16-bit address. So actually that GOTO line needs to move to line 8, or byte 8 if you like. So if you think about these as memory locations, we're using memory location 0, 1, 2, 3, 4, 5, then the next 2 locations are used for the address, then an instruction in address 8, and then 9 and 10 will be used for the high and low values of the GOTO 08 instruction. You'll see all this in a minute, so it'll all make sense. Right, so let's pop that over on the left, and what we need to do now is start basically converting all these into the binary opcodes. So that's easy enough. So the ALU 8-bit move and load immediate ones we're quite well familiar with. So for the ALU add, it's just a case of 1000, which is the opcode the class code for ALU operations, and basically then we're just giving it a function code of 001, which tells it that we want to do an add. So that's nice and easy. Next up, let's look at the moves. So the moves are straightforward again, starting with 00 and then just the destination and then the source. So first of all, we've got 010 for C as a destination and 001 for B as a source. And for line 3, we've got 001 as B for the destination and 000 as A for the source. Finally on these then we have the set ABs. So setting A to 10 is just a case of doing 01 and then follow that with 1010, which of course is 10 in binary. The next one's quite interesting. So there we're doing set AB 011 to set the B rather than A, and then we're following it with 5 ones. And the reason why we're doing this is because actually we want to use 2's complements here. So -1 is represented by just all ones. And what the set AB instruction will do is it'll actually, when it loads that, it'll actually prefix it with all ones as well. So it'll basically extend it all the way. So effectively it'll load into the register 1111, 1111. And that effectively represents -1. And it's the beauty of this then that when you add that to any of the number, effectively it'll actually take 1 off of it. Right, okay, so that's the set ABs. So let's have a quick look at the GOTOs. So for the first one on line 5, we're going to jump, loading the J register of course, if the value is not 0. And that's where the 10 at the end is. For line 8, we're going to do a jump again using the J register, but this time we're going to do it if it's 0 or not 0. In other words, we're going to jump always. Now the next bits are missing from these, and is just the address of where to jump to. So for line 5, we say that it's going to be line 3 we want to jump to, shown by the 11 at the end there. And for the GOTO instruction on line 8, we're going to jump to line 8 itself, so hence you can see the 1000 there. And this is also where you can see where line 6 and 7 have gone to, and line 9 and 10 have gone to. They're used up by that high and low value of the GOTO instruction. Cool, so that is it. We have our program ready to go. So let's go over to the computer and load it up. So we'll start by turning the computer on. And let's start with the first instruction, which is going to load register A with a value of 10, which is our starting point. We'll then load register B with -1, and then move that value from the B register to the C register. We're now into our loop. So the next thing to do then is to move A into B. With both values then in the B and C registers, we can then add those together, with the result going back into A. We then get to our jump, so I'm going to say jump if not 0, and we're going to go to the address location of 0, 3. And then if we make it past that, we'll go into an infinite loop, so jump if 0 or not 0, and that needs to come to the address of that jump instruction, which was line 8. So we should have got everything we need there, so let's reset the program counter, pair the sequencer, and let's go through the first instruction. So first thing we're expected to do is to load the value 10 into register A. And there we go, register A's got the value 10 in it. Okay, next up we should be loading B with -1. And there it is down there. And then we'll proceed then to move that out of the way into register C. So there it is there. So we've got a reasonable starting position now to enter into our loop. So the first line of the loop then, we need to copy the value from register A into register B, ready to be added. And we can see it's come through there. We can now do the add. Which gives us our value here. And you can see now that that value is 9. So we should be moving to the loop now. So here's our loop instruction to loop if not 0. We are indeed not 0, so we're expecting to do a jump here. C equals goes past 0.8, carries on all the way through. So you can see then that we have in the jump register, we have the value of 3. It's taken the jump and loaded the program counter with line 3, which means we should be going back to our move instruction, which will move the value from here to here. So I think we'll let the computer take over from here. So what we should find is that each time it will move the value over, add these two together, this will then be 1 less than before, and it should keep on going round until eventually this becomes 0, at which point the ALU should set the 0 flag, and we should then go into the infinite loop. Let's give it a try though. And you can see there that it's now got stuck on that instruction, which is exactly what we wanted. And register A contains 0. Cool. Well, that's basically it for that. So I think we'll do a bit more of a more interesting example on my summary video. But because I think you kind of like these sort of things, what I can do is, if I quickly just clear down the registers and that, and what I'll do is load address 0 back in again. So we start the program again. What I can do is, if I pop in the back, is I can set the clock speed to be quite a bit quicker. There we go, we got stuck. So where are we? Let's clock on. Okay, and let's see just how quick we can get this to go. Let's do that one last time because that was quite quick. So there you go. So I think that pretty much proves the computer can now do branching. So we'll leave that for there now. Thank you for watching.